So two main topics. First one is 3.4, which is the derivative as a rate of change. This is where we talk about velocity and acceleration, but I'm not going to spend much time on it, maybe 10 minutes or maybe 15 minutes. And then I'm going to move to the chain rule, which is 3.6, and this is covered on the midterm as well. So first one, 3.4, which is motion along a line. I will write a definition here. Let S equals f of t be the position of a moving object, Then the instantaneous velocity, at time t equals limit delta t going to 0, f of t plus delta t, negative f of t divided by delta t. Now in this definition, you can see that I'm using delta t instead of h. And it's because our variable is time. So the increment is a small amount of time, which is delta t. But you can recognize from this limit that what we mean to write here is that this is the derivative of s with respect to t. If you're given the position function, if you take the derivative of that with respect to t, that would give you the velocity. Speed is always the absolute value of the velocity. So speed would always be positive, but velocity will have a direction to it. It would be positive or negative. Positive would mean that we are moving forward. Negative would mean that we are moving in the backward direction. But speed is always positive. We take the absolute value of v. Similarly, acceleration at time t equals the derivative of the velocity. Velocity itself is the derivative of the position function. Velocity is ds dt. Therefore, the acceleration is the second derivative of the position function with respect to t, dt squared. For example, if I write suppose the position function is given by s of t equals 5t squared plus 2t plus 3. It measures the motion of a particle at any time t along this parabolic path, which is 5t squared plus 2t plus 3. Then using these definitions, I can write that the velocity equals, by definition, the notation is v of t, it's ds dt. I will take the derivative term by term. The derivative of 5t squared is 10t. The derivative of 2t is 2, and the derivative of 3 is 0. So in the end, it's 10t plus 2. And similarly, acceleration equals the derivative of the velocity. I already have the derivative of the velocity. I will have d over dt 10t plus 2, which would be equal to the derivative of 10t is 10, and the derivative of 2 is 0. So the acceleration equals 10. Now, that's all I wanted to do from 3.4. This is the velocity, this is the acceleration. You can take the derivative of acceleration as well to get a formula for the jerk, but I'm going to stop over here. There's a nice picture in your textbook that I want to draw. So before I say goodbye to 3.4, let's draw this picture. It explains the motion of an object in terms of the graph of its velocity. Suppose this is my t-axis, and I'm plotting v versus t. I'm plotting the velocity field. Suppose the graph of the velocity from t equals to 0 to, let's say, this value of t, which I will call as, let's say, t equals to t1 at this instant. This is how the graph of the velocity looks like. Let's try to guess the motion. Because I'm above the t-axis, that means my v of t is positive from t equals to 0 to t equals to t1 in this range of the time t. And my velocity is also increasing as I move from left to right along the time variable. So I can say for this region, I am moving forward because my velocity is positive. And because my velocity is always increasing, I can say that its absolute value is getting bigger, which means my speed is increasing, and I am speeding up as well. Velocity is getting bigger, and it is always positive. Now suppose from here, the graph of v of t looks like this straight line. From t equals to t1 up to t equals to t2. Now this means that my velocity is not increasing because it's fixed now, but it is still positive. So that means in this range of values of t, I am still moving forward because my velocity is positive, moving forward. I'm not speeding up, I'm not slowing down, I am going at a steady rate. My velocity is fixed now. Then from here onwards, the graph of the velocity shows this behavior. Let's call it t equals to t3. Between the time t equals to t2 and t equals to t3, you can still see that the velocity is positive. It is above the t-axis, but its value is decreasing. I'm starting from this point up here, and I'm ending up on the t-axis. So in this region, from t equals to t2 to t equals to t3, I can say that I am moving forward because my velocity is positive. But because the value of the velocity is coming down, the absolute value is decreasing, I would say I am slowing down as well. The absolute value of the velocity is decreasing. Now, as I move along, suppose my velocity does something like that. This point is, let's say t equals to t4, some value of time. Now, what is happening between t equals to t3 and t equals to t4 is that my velocity has gone negative. This means I'm moving backwards. But remember, I'm starting from 0 on the y-axis, and I have gone up to this value. If you take the absolute value of this, I can see that my speed is increasing because at this point, the speed is here. At this point, the speed would be here. As an absolute value, it would be on the other side. But I can say that in this region, then I am speeding along, speeding up, but moving backwards because my velocity has gone negative now. Moving backwards. Let's suppose it goes back and touches the t-axis over here. What can we say here now? Let's say this is t equals to t5. Now you see in this range, my t is negative. So I'm still moving backwards. But now I'm going from this point up to that point. That means the absolute value of v is decreasing. So I am moving backwards because my velocity is negative, and I'm slowing down. Okay, and now suppose it goes back to the same behavior that we started with, goes along that, I can say that it's starting to move forward again. So it's a nice description of how the motion of an object is related with, you can describe it using the sign of the velocity, whether you're moving forward or backward. And when we look at the graph, if the velocity is creeping up on the y-axis, we can say that we are speeding up or slowing down, depending on what we saw in the picture. All right. Now I'm moving forward into the next section, which is chain rule 3.6. Very important and useful. The chain rule. Before I write the mathematical statement, no, acceleration is the change in velocity. How velocity is changing with time, Jennifer, that is acceleration. How much distance you are covering in a given space of time, that measures your velocity. And how your velocity is changing in a given span of time is the acceleration. That is correct. Acceleration is the slope of the graph of v of t. Correct. Because it's the derivative of the velocity. Okay, now, here's some motivation for you. Suppose you want to take the derivative of f of x equals x minus 1 to the power 50. And I'm putting 50 deliberately here. I don't want you to think that it's possible for me to expand 50 powers. Multiply x minus 1 with itself 50 times. But this seems to be the only choice at this moment. If you want to take the derivative of this, I have to multiply x minus 1 with itself 50 times and then take the derivative of this, every term by term. But you can see that this is a lot of work. There has to be an efficient method by which we can take the derivative of this. Another example, suppose you have g of x, which is equal to sine of x plus 1 plus x squared to the power 20. Well, I know the derivative of sine x, I know the derivative of x squared, I know the derivative of 1, but this is to the power 20. I don't want to expand 20 powers of this factor and then take the derivative term by term. So we need the chain rule now. Let me write the statement and then we will see how we use it to find the derivatives of this type of expressions. If f of u, that's a variable u, is differentiable at u equals g of x, and this function g of x is differentiable at x, then the composite function, f of g of x is differentiable at x as well, is differentiable at x as well. Now here's what we mean. What we're saying is that the derivative with respect to x of the function g of x equals the derivative of f evaluated at g of x, and then you multiply it with the derivative of g of x. So g has to be differentiable at x and f has to be differentiable at g of x. This is one form in which we can write the chain rule, and it's called the composition of function form. There's another form. Now suppose that my function f depends on u. Let's write y equals to f of u. And this function u depends on x. It's a function of x. I want to take the derivative of y with respect to x. Now you can see that y doesn't depend directly on u. Y depends on u, and then u depends on x. This is called the Leibniz notation. dy dx, this equals dy du, y is a function of u, multiplied by du dx. So you connect it, or you chain it through the variable u, which is kind of the intermediate variable. Y depends on u depends on x. We want to take the derivative of y with respect to x. But I don't want you to think at this point that this u variable cancels out. We in no way mean that this du cancels out and we are left with dy over dx then on the right hand side. It's just a convenient way of writing the chain rule. Dy over du multiplied with du over dx. We are again not saying that the du in the middle cancels out and we are left with dy dx. Okay, now going back to this example. I'm going to set up this example in both ways, composition form and the Leibniz form. And after that, you can pick whichever form you like. Mostly we'll go with the composition form. The example was f of x equals x minus 1 to the power 50. Alexander, I will actually show you a shortcut. None of these forms is in my mind when I am taking the derivatives. I'll show you what I look at when I'm trying to find the derivative using the chain rule. Just give me a moment. After this slide. Okay, now first, let's do the composition form. The composition form was f g of x has the derivative with respect to x, f prime at g of x multiplied by g prime of x. First, I have to write this expression as a composition. Okay, I'm going to change the notation because I'm using f in the definition of the chain rule. Now let's take f of x equals x to the 50, and I take g of x as x minus 1. With this, now you can tell that our function h of x is the composition of f and g. Great. That means if you want to take the derivative of h, this would be the derivative of f, but evaluated at g of x multiplied by the derivative of g of x. So I need these two things. I need the derivative of f and I need the derivative of g. The derivative of f prime of x equals 50, x to the power 50 minus 1, 49. And the derivative of g of x, g prime of x equals the derivative of x is 1, the derivative of 1 is 0. I would be left with 1. Now I put everything into this formula. F prime evaluated at g of x would be equal to 50 g of x to the 49. That means dh dx equals 50 g of x 49 times g prime x, which is equal to 1. G of x is x minus 1, 50 x minus 1 to the power 49. This is the derivative of x minus 1 to the power 50. And this is how I can set it up using the composition form. I have to write two functions and express my function as a composition of those two, and then I can set it up. Now for the Leibniz notation, where we wrote the derivative of h with respect to x would be the derivative of h with respect to some function u, and then with respect to some variable u, and then the derivative of u with respect to x. Let's try to set it up this way. 49, Andy, is when you apply the power rule. Remember that we said the derivative of x to the power n is n x to the power n minus 1. You bring the power down and then you subtract 1 from it. All right. Now, suppose that my h of u now equals u to the 50. And then I take u equals to x minus 1. Okay. Now, when I put it in the Leibniz form, I need the derivative of h with respect to u. So dh du would be equal to 50 u 50 minus 1, which is 49. Remember, it's the derivative of h with respect to u. And then the derivative of u with respect to x is equal to 1 again. Therefore, the derivative of h with respect to x is derivative of h with respect to u multiplied by the derivative of u with respect to x. dh du is 50 u to the 49. du dx is 1. I put back the value of u, which is x minus 1 to the 49, the same derivative that we had in the previous case. Now, using this, we can write a rule in general. We can say, for example, that the derivative of a function of x to the power n, previously we had it as x to the power n. We can show that this would be equal to n u of x n minus 1. This is the power rule. But the extra thing that comes in is you have to multiply it with du dx, the derivative of the function that is sitting under the exponent, the base, u of x. This is an extra term from the previous power rule. Another example. And now, instead of setting it up as a composition or the Leibniz notation, I'll try to do the derivative directly, but I'll explain how. Sine x squared plus 1. Now, when you take the derivative of any expression, it involves the trig function, or it involves an exponent or an exponential, any type of function. First thing is that you deal with whatever comes in your way first. For example, in this case, when I look at this expression, it's not sine x. I know the derivative of sine x is cos x, but this is not sine x. This is sine of x squared plus 1. It's different. But at the first instant, I am not going to bother about this x squared plus 1. I know the derivative of sine is cosine, and that's what I'm going to write. So as a first step, I just write, well, the derivative of sine is cosine. I write cosine x squared plus 1. Now I multiply with it. I can't ignore completely x squared plus 1. I have to multiply with it the derivative of whatever I have inside the function now. This is where I deal with it. Now I know the derivative of x squared plus 1 would be 2x plus 0. So I get 2x cosine x squared plus 1 as the derivative. So as you get exposed to the parts of the function, you keep taking derivatives with the rules of differentiation that you had previously. Another example to expand on this. This is the first one. Second example. Suppose now my function is e to the x squared plus tan x, and I want to take the derivative of this. Okay. The derivative of e x squared plus tan x. I'm going to recall now, we said the derivative of the exponential function is exponential function again. I'm not going to bother about x squared plus tan x. I'm just going to write, using this derivative, I'm going to write my differentiation. E x squared plus tan x. Because exponential is the first thing that is coming in my way. Now I deal with the function on the top. I have to multiply this with x squared plus tan x. This is the derivative of g of x. Here, this is the derivative of g of x that we have in the general form of the composition. Now I take the derivative of x squared plus tan x. This is 2x plus the derivative of tan x is secant squared. And then I multiply it with e x squared plus tan x. That would be the derivative of e to the x squared plus tan x. Another example. Now suppose our function is e to the sine 3x plus 2. Once again, I want to take the derivative of this. First thing that I see in the function is the exponential. I'm going to apply the rule that we had for exponentials. The derivative e of sine 3x plus 2. As a first step, it is sine 3x plus 2 in the exponent of the exponential. The exponential just comes back. Now I deal with the exponent. In the exponent, I see sine 3x plus 2. Great. In the next step, e to the sine 3x plus 2. Now when I look at the derivative of sine of 3x plus 2, the first thing that we see is the sine function. So I write cosine. I do not touch what's happening inside, 3x plus 2. But then I apply the chain rule again, take the derivative of 3x plus 2. First we dealt with exponential, then we dealt with the trig function, and now we are right down to the last part, which is the derivative of 3x plus 2, and that is equal to 3. The derivative of 3x is 3. The derivative of 2 is 0. It's 3 cosine 3x plus 2 times exponential sine of 3x plus 2. That would be the derivative of the function. Now again, similarly, I can generalize this formula for the exponential, for example. We can write that the derivative of e now with a general function f of x and its exponent, that would be equal to e to the f of x. It comes back, but then you have to multiply with it the derivative of the function f of x, whatever that is. Just like in this case, we had the function sine of 3x plus 2. Okay. Another example. Let's say we're doing the derivative of 1 over 5x minus 10. With the rules that we have at this stage, we can still find the derivative of this. We can apply the quotient rule and then work out this derivative. But with the chain rule, we can simplify our work. I can rewrite this as, before I take the derivative, instead of writing 1 over 5x minus 10, I'm going to write 5x minus 10 to the power negative 1. This is exactly now the derivative of some function of x to the power n happens to be negative 1. We wrote the rule as, this is n u of x. We don't touch that, n minus 1, and then we multiply it with the derivative of u of x. So first thing now is the exponent, negative 1. I have to deal with it first. I apply the power rule. -1 comes down. I don't touch the function inside. I subtract 1 from the power. But then because of the chain rule, I will have to multiply it with the derivative of the inside part, which is 5x minus 10. This becomes negative 5x minus 10 to the -2. And then the derivative of 5x is 5. The derivative of 10 is 0. I get 5 from here. Now I can put it back in the form -5x minus 10 to the power plus 2, which is way better than applying the quotient rule and then getting the derivative out. Another trig function. Let's say we find the derivative of secant 5x. This is secant to the power 5. Let me rewrite that. This is secant x, remember, to the power 5. So again, first thing is the exponent, 5. Let's apply the power rule. 5, not touching the function inside, 5 minus 1 is 4. This is the power rule. By chain rule, I have to take the derivative of the inside part, which is secant x. The derivative of secant x is secant times tan. 5 secant 4x times secant x times tan x. Now I can put it back. Secant to the 5x times tangent of x. Okay. Let's keep doing the examples. Okay, I'm going to need a little bit of space for that. Compute the derivative of f of t equals sine t over 1 plus cos t squared. All right. We want to do the derivative of f with respect to t, which is the derivative with respect to t of this bracket sine t 1 plus cos t to the power 2. The first thing is the power 2. Apply the power rule. 2, that's my 2. I'm not going to touch anything inside. 1 plus cos t, all to the power 2 minus 1, which is equal to 1. Now I take the derivative of the inside, multiplied by the derivative of sine t, 1 plus cos t. So this is the application of the chain rule. Now, this is 2 sine t divided by 1 plus cos t. For this part, my only choice is the quotient rule now. We can do the product rule, but quotient is easier. So let's apply that. 1 plus cos t squared. 1 plus cos t, the derivative of sine t, negative sine t, the derivative of 1 plus cos t. Sweet. This is in the bracket. 2 sine t, 1 plus cos t. Let's do the derivatives. 1 plus cos t. The derivative of sine is cosine. Negative sine t. And then the derivative of 1 is 0. The derivative of cos is negative sine. All divided by 1 plus cos t. Let's simplify. 2 sine t, 1 plus cos t times cos t times 1 is cos t. Cos times cos is cos squared. Sine times negative sine is sine, negative sine squared, but I have another negative sign, so plus sine squared t. all divided by 1 plus cos t. We have this trig identity, cos square plus sine square, that equals 1. So I can write this equals, I lost the square somewhere, there. This is squared. 2 sine t, 1 plus cos t. These two give us only 1. So 1 plus cos t is what's left. 1 plus cos t squared. This cancels, the power 2. And finally, we are left with 2 sine t divided by 1 plus cos t whole squared. Yes, David, as I said, you will have lots of multiple choice questions, so you will have to match the answer. So make sure you know how to simplify using at least the basic trig identities. All right, Jennifer, I'm going to wait for a second for you. Let me know when you're done. For the long questions, it's okay. You can, you will get part marks as well, but for the multiple choice, you will have to match the answer. You will have to pick one of the choices given in the question, so you should know how to simplify. Okay, Jennifer, can we move on? Excellent. I'm going to do one more example, and then I'll leave you with an exercise. Example. Suppose we take the derivative of, with respect to theta, secant e to the theta squared plus theta squared plus 1 under the root. Okay. First thing that I see is the secant function. The derivative of secant is that'll depend, Edward. If you're asked to find the derivative, if it's forced that you find the derivative using the limit definition, you will have to use the limit definition. But if it's open, I mean, if it just the question says find the derivative of the function, feel free to use any law of differentiation, any rule of differentiation, or the limit definition, whatever you like, then it's open. Okay, now the derivative of secant is secant times tan. I'm going to apply that here. This is secant e to the theta squared plus 1 under the root times tangent e to the theta squared plus theta squared plus 1 under the root. Now I deal with the inside function. Times, by the chain rule, the derivative with respect to theta of e to the theta squared plus theta squared plus 1 under the root. I'm going to simplify this question for myself a little bit. D over d theta at theta equal to 0. In the end, we'll put theta equal to 0. Now I need to compute the derivative of this e to the theta squared plus 1 under the root. Secant e to the theta squared plus 1 under the root times tangent e to the theta squared plus 1 under the root times. Now, the derivative of exponential is exponential again. By the chain rule, I will have the derivative of theta squared with it. For the root of theta squared plus 1, first I have to deal with the root. I'm going to take away the root. Instead, I put 1 over 2. So 1 over 2, theta squared plus 1 I subtract 1 from 1 over 2, I get negative 1/2. This is the power rule. But then, by the chain rule, it has to be multiplied by the derivative of theta squared plus 1. I'll write one more step. Secant theta squared plus 1, tangent e to the theta squared plus 1 under the root, times e to the theta squared. The derivative of theta squared is 2 theta plus 1 over 2 theta squared plus 1 negative 1/2. The derivative of theta squared plus 1 is also 2 theta. And I close the bracket. This is the derivative. Now, because I'm doing the derivative at theta equals to 0, I don't need to simplify it. I'm going to put the value theta equal to 0 in it and then see what the numerical value comes out as. I simplify or I don't, it's not going to make a difference in a question like that where you're calculating the derivative at a specific value of the variable. So let's take theta equals to 0. If theta is 0, this term goes to 0. If theta is 0, this term also goes to 0. However, remember, this one does not go to 0 when theta goes to 0. This goes to 1, and this term also goes to 1 when theta goes to 0. I'm putting theta equal to 0. I'm not doing the limit. This goes to 1 at theta equal to 0. This becomes 1 at theta equal to 0 as well. But this whole thing is definitely 0. Even if these are non-zero, secant of 2 and tangent of 2, this is going to take everything to 0 in the end. So my answer would be 0 in the end. So see, I don't have to simplify in this case. I don't have to apply any trig identities. When I put the numerical value of theta, I get a numerical answer. Okay, now let's write a general expression, another one for the chain rule. Suppose you're taking the derivative of f h g of x. I'm taking the composition of 3 functions now, just to emphasize how we dealt with these different type of functions that we wrote. First thing is, function f is coming in my way. I will write the derivative of f, but I'm not going to touch anything inside. H of g of x. I kept it exactly the same. Now I take the derivative of the inside, but this is also a composition. So I multiply with it the derivative of h. I'm not going to touch inside, which is g of x. But then I take the derivative of this g of x because of the chain rule, and I finally get to the function g of x. The derivative is represented as g prime. This is the derivative of a function that is written as the composition of 3 different functions, f, h, and g. But we just keep opening up, unfolding it as we go along. Okay, now in the last couple of minutes, here's an exercise for you. Find the slope of the tangent line, which means you need to find the derivative on the graph of the function f of x, which equals square root 3x plus, there's another square root, 2 plus, there's another square root, 1 minus x. At x equals to 0. So you don't have to simplify the crazy thing that you get.